おはようございます。ちょっと間が空いてしまいましたが、朝のフーディニ作業配信を始めていきたいと思います。ここ1ヶ月ぐらいが暑くなってきたせいもあってか、なかなか夜が寝つけず、ちょっと朝の体調が良くない日が続いていて、なかなかリズムがつかめなかったんですが、ようやくそのあたりが戻ってきたので、また仕切り直してやっていきたいなと思っています。習慣的に手を動かす機会を作りたいっていうのが大きい動機なので、マイペースにまったりやっていけたらなと思ってます。はい、で、今日は、アウトライン、トゥーンシェーディングのアウトラインを使った作例で、エンタグマさんなんですけど、ちょっとやってみようかなと思います。
There is this shading technique in medical animation that was particularly popular before PBR, or physically based rendering engines, were as common as they are today, and that shading technique was to create fake X-rays. I'm sure you will have seen these before. It's become quite cliche. It's used in far too many adverts for painkillers. The idea behind this shader is that you drive the opacity and the brightness based on the angle of a polygon to your camera. So if a polygon is pointing towards the camera, like in the middle of the arm here, it becomes transparent, and if it's pointing away, like at the top here, it becomes opaque and it becomes glowing. So like I said, this is a bit cliche, but we can use a similar principle to create this kind of geometry-based toon shading effect in Houdini. So let's have a look. So here is a simple scene where I've just created a redshift light, a camera, and a background, and let's start off with a simple example using a pighead. So we'll drop down a geo container, dive inside, and in here we'll drop
今回は動画に合わせてバージョンが 19.0.498 ですね。はい。解像度めっちゃ低い。
on a pighead. So this pighead will give it an easy difficulty and will translate it to units in Y. And then let's give it some subdivisions, maybe sort of in depth of 2. Next, we'll need to give it some point normals. And sort of I. And then let's give it some subdivisions, maybe sort of in depth of 2. Next, we'll need to give it some point normals. And we
ダメだ。久しぶりで頭が回ってね。ノーマルをポイントにセットして。
can drop down our first wrangle. So in here, we're going to figure out which polygons are facing towards the camera or which are facing away from the camera. In order to do that, we need the camera. So let's drop down object merge, and in here, grab our camera, and we want the cam origin. So this is going to give you a single point, but at the moment it's at the world origin, so that's
なんで、スプレッドシートの表示なんかおかしくない？あれ？ミスった。カンマリジンまでいる。そういうことか。カメラのオブジェクトじゃないってことね。はい。
clearly not where we are. What we want to do is transform into this object, and that gives you the actual position of the.
このパラメータ初めていじった。
The camera, and that's something we can put into input too. So let's first read out that position of the camera, call it vector camera position is a point attribute coming from input stream 1. It's called the position, and we want to read it over 0.0 because it's only a single point. Next, we want to create a vector between the position of the camera and each point on our geometry. Let's call that vector dir for direction, and that's the position of the currently evaluated point minus the position of the camera. And for good measure, let's normalize that direction vector. So the next thing we're going to do is create this dot product between the direction vector and the normals of the geo. But before we do that, let's have a look at what that dot product actually is and what it is that we're calculating. Let's maybe write out this direction vector to an attribute. V at dir equals dir, and let's visualize it. And you visualize this by hitting the eye and then clicking on the particular attribute. That you want to visualize, and down here there's the visualization button, visualize there, and you go to your settings. We want it to be a marker, we don't want it to be text, we want it to be a vector trail. Now it looks as though nothing's happened, but that's because everything is pointing towards the vector trail. Now it looks as though nothing's happened, but that's because everything is pointing towards the camera that we're currently looking through. So if you move the camera, you see that
カメラから見たときの。はいはい。なるほど。
actually
あれなんか。やっぱカメラから見たとき見えないんだ。
we create a whole bunch of different vectors that are all pointing towards the camera. Maybe let's switch off the subdivide for a second so that we can see what we're doing a little bit more closely. closely. Okay, if we now also show the normals, then you can get an idea for what we're about to calculate. So the product is going to give you a value based on the alignment of that normal vector with the directional vector pointing towards the camera. So if the normals are pointing in exactly the same direction as this direction vector, the dot product will be 1. If it's pointing away, it'll be -1. And if it's pointing directly perpendicular, like it is here, it will be dot product value of 0. And so that gives you value that we can then use to manipulate things further down the line. Val for value is the dot product of the normal and our dir vector. And let's maybe switch off our normal view and our dir visualizer, and instead let's visualize that value. And so you can see that it's a positive value when it's pointing towards.
なるほど。プラス。だから、手前が、どっちだ。
The camera is a negative value when it's pointing away from the camera, and it's 0 when it's perfectly perpendicular. And you can see that as well here in the val that we've just written out. You can get rid of this temporary direction vector, we don't need it anymore. And let's go back to our shot cam position and turn off the visualizer. Okay, so now that we've calculated our value attributes, where it's 1 if it's pointing directly towards the camera, it's -1 when it's pointing directly away from the camera along the same axis as the camera pointing towards the object, and it's exactly 1 if it's perpendicular to the camera angle. So if it's facing away, let's say that side. Now what we want to do is use that value to start cutting the geometry. So let's drop down a poly cut, and we want to cut edges, and we want to cut at an attribute that we called value when it's crossing the 0 value. So if it's going either from positive to negative or negative to positive, and we want to uncheck keep polygons closed. Next, we're going to drop down another rectangle. And here we're going to create a slider that will use as our threshold for what to keep and what to get rid of. So let's say float threshold, and we'll create this threshold slider. Hit the button here to create your interface element. There we go. Let's set it to a very small value because we want everything that's really quite close to 0. So 0.0001. Next, we're going to say if that value is smaller than negative threshold, or if it's larger than positive threshold. Let's remove the point. There we go. Here we have our toon shader. Now the interesting thing is that as soon as you start moving the actual shot camera, this will update. If you change it so that you're no longer on the shot camera, it doesn't.
がよくわかんねえな。
update. And so you get this rather abstract looking object that as soon as you kind of rotate into the correct position, it becomes visible again what it actually is. And the other thing we can do as well, of course, is if we add a transform before any of this stuff in the network happens and we start rotating our pig head, then this automatically to always give you that kind of a toon shader type of outline. Now the geometry isn't particularly neat here, so let's clean it up a little by adding a fuse. And so we've gone from 2600 points to about 600 points. Great. Let's add a polypath as well to glue. Add a fuse. And so we've gone from 2600 points to about 600 points. Great. Let's add a polypath as well to glue things together a little bit better. And we want to connect the endpoints because, you know, there'll be multiple lines that are quite close together, and so it's nice to connect those. And essentially, that's it. I mean, the geometry itself is maybe a tiny bit uneven where the points are, so what we could do is drop down and resample and set that to something like 0.05, let's say, to get some slightly more even geometry here. And let's add a null for good measure. Let's call it out like point. Drop down and resample.
つなぎで、バラバラな。
Sample and set that to something like 0.05, let's say, to get some slightly more even geometry here. And let's add a null for good measure. Let's call it out. Then we head up one level. We can assign a material that I created earlier called lines. And in the Redshift tab, let's...
Hi.
Then we head up one level. We can assign a material that I created earlier called lines. And in the Redshift tab, let's go and render this. As a strand, and let's say a capsule with a tessellation subdivisions of 12 maybe, and let's hit render. So there we go. It's a little on the thin side, so maybe we want to grab our scale and bump it up a little bit. And there we
レッドショットでレンダリングしてんだ。サークルメニューどれだっけ？ Z でもない。B でもない。あれ？やべ、サークルメニュー忘れちゃった。じゃあ C なんだよ。あれ、サークルメニューなんだっけ？やべ、完全に忘れた。普通にまとめでやるか。なんかダメな気がする。そうだね、やっぱレッドシートじゃなきゃ出ないな、やっぱり。
We have our toon shader. Let's go for a slightly more complex example. Drop down another geonode, maybe copy all of our setup except for the pig head into here. And let's our toon shader. let's go for a slightly more complex example. Drop down another GeoNode. Maybe copy all of our setup except for the pig head. Here. And let's grab a file that I downloaded, which is a 3D scan that I got from 3dscans.com, and maybe reposition this slightly with a match size. So let's align it with the bottom of the y-axis and maybe make it a target size of 3 by 3 by 3 and scale to fit. So in this case, we won't need to subdivide it because it's already really quite detailed in terms of the poly count, but the poly layout itself is not particularly pretty. Although this is going to give us some maybe slightly glitchy results, it also gives you quite a lot of detail, which is really interesting. So we can get rid of our subdivide, and before we assign our normals, let's add a transform, and let's set that transform to rotate in Y by $FF. The frame value is going to be our rotation in Y, and if we set this 360, frames, put display flag on, we'll see that this is rotating 360 degrees over the course of this timeline. Now we can pipe that into our normal and the entire thing calculates. But at the same time, what I'd like to do is keep the geometry itself as well. So this entire layout is going to calculate. It's taking a little while longer now, of course, because it's much more complex geometry. Here we have our toon shader, and maybe let's branch off around after the transform. Call this out geo, and that one. this out geo, and that one out lines. Because this is rendering as redshift strands, if we also render the actual underlying geometry in the same geo container, it's going to treat that as strands, and that's not what we want. So let's add a second container here. So as strands, and that's not. In the same geo container, it's going to treat that as strands, and that's not what we want. So let's add a second container here. So call this one lines. Let's call this one geo, and add an object merge where we're grabbing the out geo. And as for material, I prepared a very simple geo material here. So we have our lines material and we have our geo material. So let's render that, see what it looks like. Yeah, like I said, it's
バカ重いな、動いて。カラーが効いてる気がしないな。
quite interesting to do this with more complex geometry because you really get that sort of toon shadery feel going all the way across. And because this is updating, if I just grab a snapshot and go to say frame 120, takes a little while to calculate. And there we go. It updates to give you a completely new toon outline. that's following the outline, and then some internal details here, like in the hair and with the eyebrows and things like that. Now, one last thing, what if you want to make sure that no matter how close the camera is, this thickness of that line always stays the same? That's quite easy to set up. We'll go into our lines geocontainer, and what we need to do is calculate the thickness of the line, which we do via the p-scale of the points on that line. We need to calculate what that p-scale is based on the distance from the camera. And so that way, when the camera is moving, it'll always be proportional to that distance. And so the line thickness will stay the same. So what we need in order to calculate the distance, well, we already have this camera being imported here. And let's, after the transform node, let's grab the center of the object. So we'll need a extract centroid, and we'll merge
セントロイド。この誰と初めて知った。
merge those 2 points. So actually the extract centroid, we need to run that over detail so we get a single point. So that's right at the middle of our geometry here. And so let's merge the points of our camera with the single point at the center. Of the statue, and let's create a line between the two. So let's drop down add sub and go to polygons by group, and now that will have created a line. And with a measure sub, we can measure the perimeter and with a measure we can measure the perimeter or the length. We want to measure it throughout, and let's call it the distance dist. So now if we click on the primitives here, we can see that we've created this attribute called dist, and in order to use that for our p-scale, we'll need another angle. Take our measure in the second input slot. Scale, we'll need another angle. Take our measure in the second input slot here, and let's first grab that distance value. So we'll need a float, we'll call it dist. For that, we need to read a primitive attribute on our input stream with the ID 1. It was called dist, and it was on the first primitive. So now let's create another slider. Let's call it a float multiplier. And let's set it to something like 0.02 maybe. And say that the p-scale is the distance times our multiplier. And if we now head up one level and render this, and if we now head up one level and render this,
ケールはちゃんと変わってるね。
We'll see that it's far too big. So let's maybe grab our global scale multiplier here and set it to 0.1. That's better. Let's grab a snapshot and lock our camera down and move in. You'll see it's still quite thin, and then if we've got our camera locked, let's move out and refresh our render. You'll see that across these different shots, the thick
P スケールの計算こんな重いわけないよ。GPU 10%使ってる。何ですか。
thickness relative to the size of the statue changes, but the thickness of the line on screen is actually the same. So how thick this is on your screen compared to how thick this is here is the same. One note is that as soon as you start moving your camera around, every time you move your camera, it's going to recalculate what the exact outline is. And so it can become a little slow. It's maybe best to switch off that mode right before you start moving around your camera to make sure that you don't slow your scene down quite a bit.
これそんな重いんだ。これでできない。あ、来た来た来た。待って待って待って、ここがつながってるから重いのか、もしかして。女子手押しだけだったらこっちの方がいいんじゃねえか。この処理そんな多いんだ。カメラ固定にしなきゃ別に大したことない。
Right, that's it. It's just a fun little setup using some old school shading techniques, but turning them into geometry inside Houdini and doing something a little bit different with it. Hope you enjoyed it. Thanks for watching and see you in the next one.
はい。というわけで、おいやら、今日は、トゥーンシェーディングのロジックを使ったジオメトリーの輪郭を抜き出して、それをジオメトリーに変換するみたいな動画をやってみました。まあ、ロジック自体はそこまで複雑ではないので、カメラのオリジンでオブジェクト自体の座標が取れるとかはちょっと知らなかったですが、ちょっとこのポリカットがめちゃくちゃ重い処理が走ってる。いまいち そのポリカットが何をやってるかっていうのが今回ちょっとあんまり分かってないですね。他は分からん。マジポリカット何やってんだこれ。いまいちマジピントがね。はい。とりあえず、レンダリングまではできましたというところで、はい。ちょっと、レッドシフトのマテリアルの設定とかはいろいろいじってみないとなんですが、一旦最低限のはい。という感じで、最低限のレンダリングまではできました。はい。ちょっとだいぶリズムが夏に慣れてき、暑さに慣れてきたので、また定期的にやっていこうと思ってます。はい。ありがとうございました。配信終わります。